You guys should all have your 1.6 handout. Okay, so we're starting out with the tangent function. Again, remember, tangent function is an odd function. So the idea is if you put a negative x value in, that's basically going to make your whole function a negative tangent x function. So just like sine function, tangent is also an odd function. So obviously we know about odd functions that they are going to be symmetrical with respect to the origin, and we'll see that same thing here, but a tangent function looks a lot different, and of course you guys can see that on your handout, how different the tangent function looks from what we saw in the cosine and sine function. Now remember, anytime the denominator is going to be 0, which means in this case, if we define tangent as sine over cosine, if cosine is 0, then we know our function is going to be undefined at those points, right? So you will actually notice at those places where our tangent function is undefined, you guys should remember asymptotes from college algebra. So you're actually going to have asymptotes at all of those places where the tangent function is undefined. And that's the reason why the tangent function is not going to be that smooth, wave function like we have for sine and cosine functions. So here, basically the idea is for values of pi halves, positive and negative, we know our function is going to be undefined at, and then of course, since these functions go in those cyclic manners, you're going to see that repeating values of pi halves where your function is not going to have any values. So you can kind of see this little table here, and they're again going from negative pi halves to positive pi halves to show you that's between those two consecutive asymptotes. Okay. All right, so the period of the tangent function is going to be pi. For sine and cosine function, your period was 2 pi. For tangent, it's just going to be pi. And of course, based on that idea of period, you can see this little equation here. We're saying that wherever your x value is going to be pi halves plus n times pi, that's where you're going to see all the vertical asymptotes at. And so that's actually going to help us when we try graphing these functions to remember at what intervals we're going to see our vertical asymptotes. Again, the domain is going to be the set of all real numbers with the exception of where you have those asymptotes, right? So again, all real numbers other than where x equals pi halves plus n times pi. Range, of course, is going to be a set of all real numbers since you're going to cover all your y-axis values. So just a quick summary here. So remember, period is 2 pi, your domain, all real numbers except those guys where you have the asymptotes, all real numbers for the range. Again, the same places where you have your vertical asymptotes, and then you can see where your x-intercepts and only one y-intercept for the tangent function. And then of course, being odd function, you're gonna have symmetry with respect to the origin. If you need to review any of these topics, you've got your little sections here. All right, so let's talk about in terms of sketching the graph here. And I've actually underlined a few things I want to make sure I highlight to you guys. So graphing this is still going to be the same kind of thing what we did with sine and cosine. You still want to find your key points to graph. In this case, we actually try to find our key points, which will be between our two consecutive vertical asymptotes. And in this case, they are talking about taking your bx minus c part and then setting it equal to those two consecutive asymptotes. So you set it equal to negative pi halves and positive pi halves. Now, this is the interesting part, which I would ask you guys to definitely highlight, is on the x-axis, the point halfway between your two consecutive vertical asymptotes is going to be an x-intercept. So you will, of course, start by identifying where your two asymptotes are going to be, and then basically halfway between that, we're going to have our x-intercept. again, they're telling us the period of the function is going to be the distance, again, between the two consecutive vertical asymptotes. So again, we know that if they ask us to do 2 full periods, that means you're having to find your other asymptotes as well. For a tangent function, and you can see based on the shape of the function, amplitude is not going to matter in this tangent. So that a value is really not going to have any kind of effect on the amplitude since it's not defined for this. And then they're basically saying once you get your 2 vertical asymptotes, you find halfway between that your x-intercept, then you can find additional points so you get that nice smooth shape of your tangent function here. And then of course, sketching your additional cycles based on that. So just starting with the basic example, y equals tangent of x over 2. So x over 2, again, what would be our a, b, c, and d values looking at this function? What is given to us? A is 1. B is 1/2, yeah, and we don't have C, we don't have D in this case. So you're actually just taking this, because this comes from that B of X part, you're taking those values and setting it equal to your negative pi halves, positive pi halves. Halfway between that would be 0, which is where you would have your X-intercept. So that's going to be at this point 0, 0. And then of course, finding a couple additional points to help us get the shape of our graph here. And of course, they're telling us once you solve this, that your vertical asymptotes are at negative pi and positive pi, right? Okay. Our example is almost similar to that. We're doing y equals tangent x over 4. Okay, so our first step will be taking that x over 4, setting it equal to negative pi halves, and x over 4 equal positive pi halves. Solve that for x, and what will we end up getting? Multiplying both sides by 4. And what do we get for x? Yeah, because 4 divided into 2 goes 2 times, so you'll end up with negative 2 pi and positive 2 pi. So that's where we're going to have our vertical asymptotes. So to do our little table, we've got negative 2 pi. What would be the halfway point between these two numbers? How would you find the halfway point between negative 2 pi and 2 pi? Yeah, subtract them from each other, divide by 2. Yeah, it's going to be 0. Yeah, exactly. So your halfway point is 0, which is where we will have our x-intercept. And then what points can we use between negative 2 pi and 0 and between 0 and 2 pi? Yeah, you could use pi, negative pi. If you wanted to include more points, you can always do, your pi halves, 3 pi halves with positive and negative. So let's say if we use negative pi and pi. So remember, the idea is you're going to be taking this value of negative pi and replacing the x in your function. So that would be y equals tangent of negative pi over 4. And what does that come out to be? And same thing for the other value of positive pi. So what is tangent It's negative pi over 4. And you can obviously also use a unit circle to help you out. Undefined? No, because the only place tangent would be undefined is at, well, at what numbers? 2 pi and negative 2 pi. Well, that's for this function specifically. I'm just asking in general for tangent. Yeah, when cosine equals 0, so that actually happens at pi halves and 3 pi halves, right? At the 90 degree and the 270. And then, of course, going in circle around it. So technically, tangent of pi over 4 will not give us undefined. Yeah, it's going to be 1, isn't it?
Yeah, it's just root 2.
Divided by root 2 over 2. Yeah, so the negative pi will give you negative 1. Positive pi will give you positive 1. Okay, so let's see how we can graph this. Okay, so again, I'm going to do a longer x-axis. And let's say we're going from 0, 0 to pi to 2 pi. And you know, normally they always ask you to do 2 full periods. All right, so let's see, we're going to have our vertical asymptotes at positive 2 pi and negative 2 pi. So where do you think our next set of vertical asymptotes will be? Negative 4 pi and 4 pi? Does that sound right? Nope. Look at the distance between negative 2 pi and positive 2 pi. That's a distance of 4 pi, right? So if we talk about the period of this function, you're looking at a 4 pi. So that means you would actually have to extend this out, and I wish I'd drawn my graph longer now. You're going to have to go actually to 6 pi and negative 6 pi, because between each vertical asymptote, you're going to have this distance of 4 pi. So let me see if I can erase some of this stuff out and start over. Okay. If we did pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, there we go. Negative 2, 3, 4, 5, 6. Technically, this would actually make it 3 periods instead of 2. All right, so at 0, 0 is our x and y intercept. At pi, we were at positive and negative 1. So about here and here. So how would that translate into this other period? So again, remember, you are going to hit your vertical asymptote here. And then when you get to that 2 pi, you will hit another vertical asymptote there. So you should have that kind of shape on that. So if I was looking at 3 pi and 5 pi, where would my values be for them?
So 4 pi
Would be the 0, good.
and then 5 pi would be positive 1, and
Good.
3 pi would be negative 1.
Very good, yeah. So just repeat that pattern. So technically this would be our 2 full periods, and then if you replicate that on the left-hand side, you would have the same thing here. Okay. Normally keep in mind, they will ask you to do at least 2 full periods. All right, question on this graph here. Okay, your next example is looking at y equals -3 times tangent of 2x. So of course your -3 would technically what we call as the amplitude, but since tangent functions don't have amplitudes, we're going to leave them as it is, and then of course your 2x will be the bx part. So again, we start by taking 2x, setting it equal to -pi-halves, positive pi-halves, solve that so that you can get your x values. So at -pi-4s, we'll have again vertical asymptote, positive pi/4 vertical asymptote, and then halfway between that again would be our x-intercepts, and then we've got a couple other points to help us out here. Now in this case, since you have that negative in front of the 3, you will notice that the direction of our graph has changed, right? Because what is that looking like now? Yeah, very nice. So you're actually looking at the reflection. If you didn't have that negative in front of the 3, this graph would basically be reflected on the x-axis, and you would have that same shape like we saw in our example 1 here. So because of that negative, the direction of your tangent function will change. So our graph is again a pretty simple example here. They're asking you to find y equals tangent of 2x. So we're not going to be seeing reflection in this. So how would your answers come out to be in this case? What would that graph look like? So we did x/4 in example 1. This guy is 2x. What will that look like? Will we have a shorter period, a longer period? You know, how is that going to get affected? It will be a smaller, shorter period, yeah. Okay, so let's look at tangent of 2x. So again, take your 2x, set it equal to -pi-halves, and 2x equals positive pi-halves. What kind of x values do we get? Yeah, it's going to be the same. We're dividing both sides by 2. Okay. Where is your halfway point going to be at? Yeah, you're still going to be 0. That's your x-intercept. And what values, again, can you use in middle of -pi/4 and 0? 0 and pi/4. You could do pi/6. I actually used pi/8, but let's try with pi/6 and see what we come up with. So what will you get for pi/6? Say that one more time. You're not going to get a whole number answer or an integer. You get a decimal. Okay, what did you come up with then?
It's like what is like root 3? So it's like 1.7320.
And this is for positive or negative? I'm not getting that. I'm getting 0.577.
And it's because we didn't multiply by 2. Once you multiply by, so it's tangent.
Oh, that's right. Thank you. I did not do that. Can't believe I didn't do that. Yeah. All right. Thank you so much. So that would be positive square root of 3 then? And what do you get for the negative? Oh, come on. You don't really need to calculate. This is an odd function. It's going to be negative square root of 3. Use that idea of this being an odd function. Alrighty, so let's see. So at negative pi fourths, positive pi fourths, we have our vertical asymptotes. So where will be our next set of asymptotes at? Three pi over 4?
So it would be like a pi, 4 pi, so it would be 5 pi over 4. And negative 5 pi over 4.
Negative 5 pi over 4. Okay, so let's think about this. Our period here is going from negative pi over 4 to positive pi over 4. What is that distance? Sorry. Pi over 2. Okay, so if you add pi over 2 to pi over 4, what will that give us? Okay, pi over 4 plus pi halves. You said 2 pi over 4? So pi halves? Okay. So that means, come on, think about this.
No, that's correct.
Yeah, it is right.
That is right.
Okay.
It's probably because you use pi over 6 like in the middle.
No, yeah, 3 pi over 4. I'm blaming it on the cold, okay? Alrighty. Well, good. I'm glad somebody knows what they're doing today. Alrighty. I don't know. I kept adding it wrong. I was like, what am I doing? It's not adding.
What did you get?
I was actually getting 5 pi over 4, and I was like, how is pi plus half? I mean, pi half and getting me to 5. I was like, okay, this is completely wrong. All right, so we're at 0, 0. Let's see, pi over 6, which will be just a little less than halfway between 0 and pi over 4 will be at, well, approximately 1.7, right? So if we do this as 1 and negative 1, maybe positive 2 and negative 2, you're looking at, I don't know. Okay, positive somewhere over there, 3/4 of the way. This will be negative pi over 6, so maybe somewhere down here. We are looking at, and again, you're still going in the, it should be going somewhere like this. And then something like this is what you should be seeing on your graph. Now, one thing I did want to mention to you guys that, of course, I am drawing my graphs freehand, but we do want to use a ruler, a scale to kind of get even spacing between our x-axis, between our y-axis. So even though I am drawing this freehand, I would definitely recommend you guys to use a ruler, get your straight lines, get equal distance between your x values that you are using, because otherwise, as you can see, my graphs don't come out looking nice just because I'm doing this freehand and they're all over the place. Alrighty. Okay. So they're talking about comparing the graphs in examples 1 and 2, and basically it's talking in terms of what happens when your b value is between 0 and 1, and what happens when your b value is greater than 1. So even the examples we did for 1 and 2, you did a tangent of x equals 4 or tangent of 2x. So the idea is when your b value is going to be between 0 and 1, which would be your x over 4, your period actually is going to be greater, right? Because we got a period of 4 pi when we did that. But when you did a tangent of 2x, our period was just pi halves, right? So when it's greater than 1, your period is going to be smaller than when your b value falls between 0 and 1. And then, of course, we kind of looked at this with examples 1 and 2. When your a value is greater than 0, we're talking about, the graph will increase between the vertical asymptotes if a is greater than 0 and decrease, because you're actually looking at that reflection if your a value is going to be negative. So like we saw in example 2, where you had that -3 in front of our tangent function, so our graph was decreasing, which meant you had that reflection on your graph. And then, of course, you can also think in terms of your horizontal stretch and shrink with your b values when your b is between 0 and 1 or b is greater than 1. Now, your cotangent function, of course, is the reciprocal function of the tangent function. So you will see a lot of similarities between those two. They still have the same period. So your cotangent function also has a period of pi. And then, of course, for a cotangent function, since we define it as cosine over sine, anytime your sine function is 0, your cotangent function is going to be undefined. So normally, where is our sine function 0 at?
0.
At 0 and?
0. 0.
Pi. Right? So again, think in terms of a unit circle. And so you will notice here that since our vertical cotangent function is undefined at 0 and pi, then that means that at intervals of n times pi, you're going to have vertical asymptote. So basically at pi, 2 pi, 3 pi, 4 pi, right? All of those, and same thing on the negative side, you're going to have your vertical asymptotes here. And then in this case, since our vertical asymptotes are going to be at 0 and pi, we take our bx minus c part of this problem and put it equal to 0 and pi. So again, the domain for a cotangent function is going to be all real numbers except the places where we have our vertical asymptotes at, which is at n times pi. Range will again be negative to positive infinity. You can see your x-intercepts here at pi halves plus n pi, and then same thing, it's an odd function, so symmetry with respect to the origin. So what are we noticing here in the cotangent function? It is a decreasing function, isn't it? And it actually looks very similar to what we saw in example 2, where you had that negative 3 times tangent of 2x because of that reflection, right? And with cotangent being a reciprocal function, by default, it is actually a decreasing function here. So the example we are looking at is y equals 2 times cotangent of x over 3. So again, you've got that positive 2 in the front. Your b value is 1/3. So we start by taking our x over 3, set it equal to 0, and set it equal to pi. So that actually gives you x equals 0 and x equals 3 pi. So in this case, your period is now 3 pi, and your vertical asymptotes are going to be at 0 and 3 pi. So again, find your x-intercepts, find a couple different points, and you can try and graph this. So what do we notice here in terms of similarity between our tangent function when you look at that table? Anybody catch that? Okay. Same thing as tangent, halfway between your x values, you're going to find your x-intercept. So same thing, take your distance between 0 and 3 pi, and right halfway between that is your x-intercept, which happens to be at 3 pi over 2 in this case, and then they're basically taking points halfway between those intervals and coming up with other points for this function. So let's see if we can replicate that for our cotangent function here. Y equals cotangent of x over 4. Excuse me. Okay. Remember, for cotangent function, you take your x over 4, set it equal to 0, and x over 4 equal to pi. And what will those x values come out to be? Yeah. Okay, so this guy obviously has a period of 4 pi, right? Okay, let's find our values here. So at 0, we have our vertical asymptote. At 4 pi, we have our vertical asymptote. What would be the halfway point here? Very good. So at 2 pi will be our x-intercept, so that will be 0. And what are those points we can use between 0 and 2 pi and 2 pi and 4? Yeah, you can do pi and 3 pi. So what is cotangent of pi over 4 and cotangent of 3 pi over 4? 1 and -1? So 1 for pi, you said? And okay. Okay. Again, let's see what this graph will look like. So we are going from 0 to pi, 2 pi, 3 pi, 4 pi. And they're actually asking us, they didn't say that in the example, but they're asking us to do 3 cycles and 3 periods. So if we're going from 0 to 4 pi for our asymptotes, where will be your next asymptote at? Very good. Okay, so since I actually have an asymptote at x equals 0, which is actually that y-axis, right? At 4 pi, 8 pi, negative 4 pi, then let's see, at 2 pi, we have our x-intercept, which means your next intercept would be at 6 pi, right? And then same thing on the negative side. For pi and 3 pi, we are at positive 1 and negative 1. So positive, negative. So these are your cotangent functions. So they're going to look like this. Those would be your 3 cycles. And I'm actually adding a 4th one. It's supposed to be a little bit more curvy than what I'm drawing them. But, you know, obviously try and do your best that you can. So you can kind of see, I mean, the steps are still pretty much the same, right? Your graph just looks a little bit different. And then for your tangent and cotangent functions, we are having to take those bx minus c part of our equations and set them equal and solve them for x, right? So for tangent, you set it equal to negative pi halves to positive pi halves. For cotangent, we're doing it for 0 and pi halves, right? Because those are the values where we typically reach a 0 value for our cosine or sine functions, depending on if you're looking at tangent or cotangent. So any question about this graphing that we've done so far? Are we doing okay on this? All righty. So you know what? I think we'll stop right here for today.